So here we now look at an even more special case of free fall known as vertical projectiles, where instead of our object being launched with a horizontal velocity, our object is now launched with a mix of a horizontal and vertical velocities, hence why we call it a vertical projectile, our topic for 1.7. So the major features of vertical projectiles. All of the major features from horizontal projectiles still apply. Independence of horizontal and vertical directions, a constant horizontal velocity, and thus a zero horizontal velocity. The only thing that is changing is that now there is an initial vertical velocity in addition to initial horizontal velocity. So as we can see from this graph right here, when we throw our object, after our object is thrown, it will be in a state of free fall, as the only thing influencing the object's motion is the acceleration due to gravity. After the ball loses contact with our hand no longer influences the motion. Okay? So we can see right here, if we throw it up with 19.6 meters per second, that means the acceleration due to gravity is going to slow our object down in the vertical direction at a rate of 9.8 meters per second until we reach the top, at which point our vertical velocity is briefly zero because now our object is changing direction in the vertical direction. Okay? Again, this goes back to the idea behind free fall, is that when we change direction in the vertical direction, we're going from rising to falling, which means our velocity goes from positive to negative, and hence our vertical velocity is briefly zero. Now, we still have our horizontal velocity throughout, because our horizontal velocity, as we've talked about, is not affected by the acceleration due to gravity. So even at the top, we are still going to have some velocity in the form of our horizontal velocity. So the only thing that's happening is the vertical velocity is briefly zero as we change direction in the vertical direction, but in the horizontal direction, we still have a velocity at the top in the horizontal direction. So the vertical acceleration is still negative g. Again, the idea being is that gravity still acts in the vertical direction at all points throughout our trajectory in order to slow our object down as our object heads upward, and then as our object's falling to speed our object back up. So here we're going to apply trigonometry to projectiles. The idea behind a vertical projectile problem in terms of analysis is that we're going to be given some initial vertical velocity, and we're going to have to break it up into, we're going to be given some initial velocity, and we have to break it up into a vertical component and a horizontal component, so that way when we apply kinematics, we have initial velocities in the x and y directions. So the main idea here is that if we have some initial velocity v naught, okay, v naught right here, it's not labeled right here, but we can still just kind of take the v naught and put it right here. That means that if we throw it with an angle theta, that means sine of theta is going to be equal to opposites, aka our initial vertical velocity, divided by our hypotenuse, which is going to be our initial overall velocity. So we're going to have sine of theta equals our initial vertical velocity divided by our overall velocity. So we're going to get that our initial vertical velocity is equal to v naught sine of theta, just applying a little bit of SOHCAHTOA from trigonometry. Likewise, with the x direction, with the horizontal component of velocity, we see that cosine of theta is going to be equal to adjacent, or our initial horizontal velocity, divided by our hypotenuse, our initial overall velocity. So we have cosine of theta equals v naught of x divided by v naught, our initial horizontal velocity divided by our initial overall velocity. So our horizontal component of our velocity is going to be equal to v naught times cosine of theta. And thus, applying a bit of trigonometry, we can determine what our initial velocities in the x and y direction are, provided some initial overall velocity in a problem. So let's look at problem-solving strategy for vertical projectiles. The kinematics process is still overall the same, except the first step that we're going to do now is we're going to determine the initial horizontal and vertical velocities. Following that step, we now proceed through all of these steps that we usually follow with kinematics. We write down all our knowns and unknowns for separate x and y directions, and we identify what the problem is asking us to solve for. Third, we determine which equations we need to use. Fourth, if needed, again as we saw with horizontal projectiles, we switch directions to find time. Time is the bridge between the two directions again. And then lastly, we solve for your unknown in your original direction. So let's look at what this looks like in practice. So suppose a baseball is hit at an angle of 45 degrees with an initial speed of 30 meters per second. At what distance from home plate will the ball hit the ground? This person actually looks like they're throwing a horseshoe, but whatever, it works for us, okay? So the first thing we're going to do is we're going to determine our horizontal and vertical initial velocities. So we know our initial velocity overall is 30 meters per second. So that tells us v naught x is going to be equal to v naught times cosine of theta, or 30 meters per second times cosine of 45 degrees, 21.21 meters per second. Likewise, our initial vertical velocity is going to be our overall velocity times the sine of theta, so we're going to have 30 meters per second times the sine of 45 degrees, which equals 21.21 meters per second. In this case, this actually makes sense because the sine of 45 and the cosine of 45, if you remember from Algebra 2, are both rad 2 over 2. So we'll get the same horizontal and vertical velocities in this scenario. But in general, that is not always the case. So now we go to step 2, we write down our knowns and unknowns. We know in the x direction, we always start measuring from a height of 0, or excuse me, a position of 0. We know our initial horizontal velocity is 21.21 meters per second, and we know our initial horizontal acceleration is going to be 0, again because there's nothing influencing our motion in the horizontal direction. In the y direction, our initial height is 0, okay? For these vertical projectile problems, your initial height will always be 0. Our final height is going to be 0 because the ball returns to the ground when all is said and done. And then we know our vertical acceleration, again, is the usual negative g. And our initial vertical velocity is 21.21 meters per second. And then our unknown is how far away our object will hit the ground. So let's wait for this little thing down here to go away. So in step 3 then, we see that for x, we're going to need x naught plus v naught x times t plus 1/2 of our horizontal acceleration times the time squared. Now again, just as the case with horizontal projectiles, okay, we see that we do not have time available for this equation, so we need to go to our y direction to solve for time. So we're going to use y equals y naught plus v naught y times t plus 1/2 of our vertical acceleration times t squared in order to solve for our time in the y direction. Again, this is the same general process we followed with horizontal projectile problems. It's just now that we have to make the modification of calculating out what our initial horizontal and vertical velocities are. So now, in step 4, we go to the y direction to solve for time. We know our initial height is 0, or excuse me, our final height is 0. We know our initial height is 0, so we can cross those out to get 0 equals our initial vertical velocity times time minus 1/2 of our acceleration of gravity times t squared. So now what we're going to do is we have a common term of t here. So what we can do, just like we do with polynomials in Algebra 2, is factor out this t right here so that we have v naught y minus 1/2 g times t outside of the parentheses equals 0. So that's going to give us two separate times for t. T equals 0 for this corresponding factor right here. And then we're going to get v naught y minus 1/2 gt equals 0. So we're going to get t equals 2 times our initial vertical velocity divided by acceleration due to gravity. And when we plug in our known information, specifically that the initial vertical velocity is 21.21 meters per second, and we divide by the acceleration due to gravity, that tells us that our object is in the air for 4.24 seconds. Now, you may be wondering, what does the t equals 0 refer to? Why do we get two different times? Well, if we think about it, we're solving this specific scenario right here for when our object is at ground level. And there are two different times when our object is at the ground level. At t equals 0, when the object is initially thrown from the ground, and at t equals whatever time, in this case 4.24 seconds, when our object returns to the ground. So you'll get two different times here. You'll always get t equals 0, and then you'll get a numerical value for t. The numerical value of t is the value that we are interested in. So now we move to our last step. We have found t, okay? So we use that again with our kinematics in the x direction in order to solve for our distance. So x equals x naught plus v naught x times t plus 1/2 axt squared. Again, x naught we said equals 0, and we know our horizontal acceleration is 0, so that leaves us with x equals our horizontal initial velocity times time, or 21.21 meters per second times 4.24 seconds. Thus, we get that our distance traveled in the x direction is going to be 89.9 meters. And thus is the standard problem solving process for a vertical projectile.